All right, today we're going to tackle a true classic. You've probably seen this one in coding interviews. It's that problem that seems simple on the surface but gets tricky fast. I'm talking about trapping rainwater. It's a fantastic puzzle, so let's just dive right in.
So just look at this picture for a second. Imagine it just poured rain. You can see how the taller bars create these little valleys, right? The question is, how much water is actually stuck in there? I mean, just eyeball it for a sec. What would you guess? This is the exact puzzle we're going to break down and solve, step by step. Okay, so let's put this into programmer terms. What we're really given is just an array of numbers. Each number is the height of one of those bars, and we're told to assume each bar is, just 1 unit wide. Our mission? To write some code that computes the total amount of water that can get trapped in those dips. Simple as that.
And here it is. This is the exact array we're going to be working with. Each of these numbers, 4, 2, 0, and so on, maps directly to the heights of the bars we just looked at. So keep this example front and center in your mind, because we're going to use it to test out a few different ways to solve this thing.
All right, so whenever you're faced with a new problem like this, where do you even start? Well, a great place is always the most obvious, straightforward approach. The one that just kind of makes sense right away. It's probably not going to be the most efficient, but that's okay. It helps us wrap our heads around the problem. We call this the brute force way.
The logic here is pretty intuitive if you think about it. Pick any single bar. How much water can sit on top of that specific bar? Well, it's trapped by its walls, right? The water level can only go as high as the shorter of the two walls containing it. And what are those walls? It's the tallest bar somewhere to its left and the tallest bar somewhere to its right. So the formula is simple. Find max left, find max right, take the smaller of those two, and then subtract the height of the bar you're currently on. That's the water for that one spot. Then you just do that for every single bar and add it all.
Sounds simple enough, right? But here's the catch, and it's a big one. To find the max left and max right for every single bar, we have to scan the array again and again. That's basically a loop inside of another loop. In big O notation, that's O of n squared. And trust me, for a really big input, that is just painfully slow. We gotta do better.
So we're at a classic crossroads here. Our brute force method is slow, but hey, it's super memory efficient. It doesn't use any extra storage. This brings up one of the most fundamental trade-offs in all of computer science. What if we could make it faster by using a bit more memory? Are we willing to make that trade? Can we sacrifice space to gain some speed?
And the answer is absolutely yes. This leads us to our next approach, the pre-computation method. The idea here is really smart. Instead of finding the left and right maxes over and over again, why don't we just figure them all out once, right at the beginning, and just store them somewhere? Okay, so here's how we do it. First, we make a whole new array, let's call it left max. We'll walk through our original array from left to right, and for each spot, we'll record the tallest bar we've seen so far. Then, we do the exact same thing, but for our right max array, going from right to left. Now we have these two handy helper arrays. All we have to do is loop through our heights one last time, and for each bar, we just look up the answer in our left max and right max arrays. No more rescanning, the calculation becomes instant.
And bam, this is a massive improvement. Our time complexity is now down to O of n. Why? Because we're just making a few separate passes over the array. No more loops inside of loops. But, just like we talked about, it came with that trade-off. We had to create two new arrays, which means our space complexity is now also O of n. We're using extra memory.
So, this is way, way better. But in interviews and in the real world, the truly elegant solution is the one that's great on time and space. So the perfectionist in all of us has to ask, can we do even better? Is it possible to get that sweet, sweet O of n runtime without using all that extra O of n space? Can we get the best of both worlds?
You bet we can. And that brings us to the final, most elegant solution. Honestly, this is the one that interviewers are really hoping to see. It's a beautiful trick called the two-pointer technique, and it lets us solve the entire problem in just one pass with no extra arrays at all.
Okay, so here's the key insight, the real aha moment for this whole problem. Remember how we said the water level is limited by the shorter of the two big walls on either side? Well, that means we don't actually need to know the tallest wall on the left and the tallest wall on the right at the same time. We only care about which side is the bottleneck. As long as we know the wall on the other side is taller, we can make a decision based on the shorter side. That's the limiting factor.
So, to make this magic happen, all we need are 4 simple variables.
We'll set up a left pointer at the very beginning of the array and a right pointer at the very end. Then we just need 2 more variables to keep track of things as we go. Left max, which is the tallest bar we've seen so far coming from the left, and right max, the tallest we've seen from the right. That's it.
All right, let's actually walk through our example step by step. So left starts at index 0, right starts at index 5. First things first, we compare the heights at our pointers. The left height is 4, the right is 5. Since the left side is shorter, we're going to process the left pointer. We see the height is 4, so we update left max to 4. Then we move our left pointer 1 step to the right to index 1. Now at this new spot, the height is 2. Is that smaller than our left max of 4? Yes, it is. So we can trap water here. How much? It's left max minus the current height, 4 minus 2, which is 2. We add that to our total. See the pattern? We just keep repeating this, always looking at the shorter side and moving that pointer inward.
So we just keep this dance going. Compare, calculate, move the smaller pointer in. Compare, calculate, move in. We do this over and over until the left and right pointers finally meet in the middle. And when they do, we've added up all the little bits of trapped water and we get our grand total, 9.
And that just shows you how powerful this 2-pointer trick is. Think about what we just did. We got our time complexity down to a beautiful O of n because we only went through the array once. And our space complexity? O of 1, constant space. We just used a few variables, no extra arrays needed. This is it. The best of both worlds. The optimal solution.
So why is this problem such a darling of technical interviews? I mean, why do so many companies ask it? Well, it's because it's not really about just spitting out the number 9. It's about the thought process, the journey you take from a clunky first idea to an elegant final one.
When an interviewer gives you this problem, they get to see a whole movie of how you think. Do you start with that simple brute force idea? That's a good sign. Do you recognize that it's slow? Even better. Can you articulate that classic time versus space trade-off? Awesome. And then, can you make that final leap to the clever, optimized 2-pointer solution? It's like a whole problem-solving obstacle course packed into one single question. And you know the best part is, once you really get the logic here, especially that 2-pointer technique, it's not just for this one problem. It unlocks a whole family of other tricky questions. Problems like container with most water, or largest rectangle in histogram. They all use similar ways of thinking, so mastering this really pays off.
So, congratulations! You can now trap rainwater on a 2D map like a pro. But that leaves us with one last, really fun question to chew on. What if this wasn't a flat line of bars? What if it was a 3D grid, like a landscape of skyscrapers? How would you even begin to calculate the water trapped in a 3D world? Now that's a challenge to think about for next time.